Howdy! I miss our interactions, I miss our class, I miss you guys, so I decided to record several problems on conservation of linear momentum that might be helpful for you. And one of these problems is problem from second exam that was given in 2018. And this problem says that there is a sled of mass m3. It is sliding on icy, frictionless, that's important, horizontal surface with velocity of magnitude v naught. There are two riders on the sled, rider 1 with mass m1 and another one with mass m2. They both decide to jump off the sled. Their horizontal velocities are known and they are shown here. So v1 at theta 1 and v2 at given angle theta 2. The question is, what is velocity of the sled after they jump off? First question that you need to ask yourself, which law will you use to solve this problem? Well, you will use conservation of linear momentum. Why? Because conservation of linear momentum tells you that dp total dt is equal to F external force. Now, this interaction happens on frictionless surface. So external force, force of friction, this is top view, force of friction is 0. Then momentum is conserved, and p momentum is a vector. I break it into components. Px before these two jump off has to be equal to px after, and py before is equal to py after. Important thing is that now, after you write it in components, you have to specify your coordinate system. This is my x, this is my y. If you don't have coordinate system, then I don't know what you mean by projection of momentum on x and on y. Now we are ready to write the total projection of total momentum in x direction. So we have a rider with mass m1 and rider with mass m2 and the sled with mass m3. They all move with the velocity that is along x. So projection of v naught on x is just v naught, and it is known. That's why I put v naught here. This is my left-hand side of this equation, px before. It is equal to px after. What do we have after these two people jumped off the sled? We have momentum in x direction for the rider 1, which is m1. Then projection of velocity v1 on x will give me v1 cosine theta 1. Then I will have second rider plus m2 v2 cosine theta 2. It's important to keep these indexes because these masses and velocities are different. And we have unknown plus I have m3, and I don't know velocity of the sled after the this jump. So since I don't know it, I will bring this plus again here. Since I don't know it, I call it v sub x. And that's what we need to find. Velocity of the sled after this jump. Now what do we have in y direction? This is px before is px after. In y direction we have py before is 0, nothing in y direction. Py before is 0. And py after we have m1 v1 sine theta 1. Projection of velocity v1 in y is positive. Projection of velocity v2 in y is negative. That's why I put here minus m2 v2 sine theta 2. And again, I don't know the velocity of the sled after this jump. So I call it v sub y. I remind you that what we need to find velocity of the sled after, and velocity is a vector. So if I know x component and y component of velocity of the sled, this means that I know the velocity. And look at this, it's system of equations. Two equations and two unknown variables, vx and vy. We can solve for vx from the first equation, we can solve for vy from the second equation, and that will be our final solution. So what is v sub x? V sub x from the first equation is m1 plus m2 plus m3 v naught minus m1 v1 cosine theta 1 minus m2 v2 cosine theta 2 divided by m3. What is vy? Right here. Vy is equal to, I bring this guy to another side of the equation with plus m2 v2 sine theta 2 minus m1 v1 sine theta 1 divided by m3. So I found x and y components of velocity. The problem is solved. So what will be my final velocity of the sled? It will be vx unit vector I plus vy unit vector j, where vx and vy are boxed here.